Hi everyone, thank you for taking a look at my poster. My name is Aarya Venkat. I'm at the Cannon Lab in University of Georgia. My project is looking at the hydrophobic cores of glycosyltransferases. Hydrophobic cores are fundamental structural properties of proteins. They're largely associated with protein folding and stability, but a number of studies have recently come out suggesting roles involved in protein evolution and function. The first step we take is actually categorizing the GTA hydrophobic core as three distinct modules that have evolved over evolutionary time. The first is the phosphate binding cassette, which essentially binds the nucleotide diphosphate donor that all GTAs bind. If you take a quick look at Figure 1, Panel D, you'll notice that this phosphate binding cassette, or PBC, is actually found in a lot of different nucleotide phosphate binding enzymes. These are HPR kinases, hydrolases, oxidoreductases, and epimerases, to name a few. The next stage in GTA evolution is the addition of a Rosman fold core through the end lobe. Through sequence analysis, we've found that all of these residues are actually conserved across all Rosman fold enzymes. Finally is the addition of a GTA-specific C-lobe tether. It's actually placed right behind the catalytic site, and it essentially allows the alpha F helix to be tethered to the phosphate binding cassette. The alpha F helix contains the XED catalytic base for catalysis to occur. So naturally, our question was whether or not this tether could be involved in catalytic activity. In fact, we found a lot more. We found a correlation of this tether with mechanistic divergence. One of the key factors that divide GTAs is their mechanism, whether they retain or invert the stereochemistry of the glycosidic linkage. Specifically, the tether is made of two residues, and we're looking at the minimum distance between these residues. And we find that most inverting GTs essentially form a contiguous core. Those GTs continuously have a hydrophobic contact between these two residues. The hydrophobic contact is defined as somewhere between 4 to 7 angstroms. Retaining GTs, on the other hand, are sort of all over the place. There are some, the vast majority don't maintain a contiguous hydrophobic contact, but a few do, and most of the ones that do are actually, we found through sequence analysis and phylogenetic analysis, GT2 related. GT2 is one of the most ancestral GTAs, and the fact that some retaining GTs are closer to GT2 and some are much farther might indicate or might support multiple independent evolutions of the retaining mechanism. This tether is actually really variable across families, but pretty well conserved within families. Panels D and E show a salt bridge in this tether rather than a hydrophobic residue. Panel F, GT31, shows a threonine in this residue rather than a hydrophobic residue. Through the Mormon lab, we had access to GT31 in that particular threonine residue, so we wanted to make some mutations in that threonine to essentially see whether or not those specific variations contributed to catalytic activity. We ran a computational and experimental screen, and indeed, in Figure 3, you can see in Panel D, we actually discover that one of our mutants, which mutated the threonine back into an isoleucine, increased catalytic activity. In Figure 4, we ran molecular dynamic simulations of this to figure out why exactly catalytic activity was increased. In our MDs, we identified two unique conformations of the catalytic base, D-in and D-out. In D-in, the catalytic base is pointed inwards and is actually interacting with the threonine with a water molecule. In D-out, it interacts with the substrate complex. When you mutate the threonine to an isoleucine, there's no longer a hydrogen bonding interaction. And in Panel B, we showed 12 MD simulations where we definitively show that there is a conformational shift in occupancy to the D-out conformation when you mutate to an isoleucine. We ran these molecular dynamic simulations for 1 microsecond per replicate, so 12 microseconds in total. What this suggests is that the evolution of a threonine in B3GNT2, this GT31, may be a mechanism to regulate catalytic activity by essentially shifting the conformational ensemble of this XED catalytic base towards a equal distribution of D in to D out, where it's not so close to the substrate complex as often. In summary, we're talking about the canonical GTA, which we can separate into three distinct modules: the PBC, the Rosman end lobe, and the GTA-specific C-lobe tether. The addition of the C-lobe tether anchors the F helix and XED catalytic base to the PBC. Multiple mutations that we made on this tether expressed well and retained thermostability. So it's possible that this might actually open up a path to synthetic design of GTs. And finally, the evolution of a threonine suggests a possible mechanism to fine-tune this catalytic activity. And so this presents an interesting quandary. Could we engineer regulation into other GTs as this GT does with its tether? Thank you for listening, and please take the time to look at my poster in full. Thank you to the NIH, the ARCS Foundation, and to Society for Glycobiology meeting.